Question 5 is a relatively straightforward question to do with entropy and free energy. And if you've revised that, it's one of the easier questions on what was overall quite a challenging paper here. So the first question, we've just got to explain for each process why delta S has the sign indicated. So for process A, you can see we've got 3 moles of gas on the left, turning into 2 moles of gas on the right. So the reason that delta S is negative is that there's a decrease in the number of moles of gas, and therefore a decrease in the disorder in the system. Remember, gases are disordered things, so the more moles of gas you've got, the more disordered the system is. So what you say is that there's a decrease in the number of moles of gas, and therefore a decrease in disorder, is why delta S is negative. In B, we've got a liquid turning into a gas. So what you say is that the gas is more disordered than the liquid, and therefore the entropy increases when you turn liquid into gas. Okay, gas is more disordered than the liquid. In part C, we've got gas turning into liquid. So it's the reverse this time, that we're going from the highly disordered gas state to the less disordered liquid state, and therefore delta S is negative. And finally, in the fourth one, you can see again this is a change in the number of moles of gas. The solid, its entropy is negligible compared to the gas, it's much more ordered. So what we focus on is that the number of moles of gas is increasing, that we're going from 1 mole of gas to 2 moles of gas, and therefore the extent of disorder in the system is also increasing. Right, part B is all the standard calculations that you've practiced. It was just a little bit trickier because you had to knit them all together. It didn't sort of take you through it rather step by step, but they're all the standard entropy free energy calculations. So first of all, you've got to calculate the overall entropy change for the reaction. So remember, the way you do that is to say that delta S is equal to the entropy of the product minus the entropy of the reactant. Because the change is at the end you have got the entropy of the product, but you've lost the entropy of the reactant. So that's equal to, you just look up the numbers from the table, so you've got 40 plus 214 is the entropy of the product, minus 89 is the entropy of the reactant that you're taking away, is 165 joules per Kelvin per mole, but it asks you to show that it's 0.165 kilojoules, and obviously that's because you have to divide by 1,000 to turn joules into kilojoules, so that's 0.165 kilojoules per Kelvin per mole. Okay, and that's got the first bullet point dealt with. Then it says that we've got to show that calcium carbonate is stable at 25 degrees C. If it's stable, it means it doesn't decompose. So what we've got to show is that that decomposition reaction is not feasible. Okay, so in other words, we've got to show that for this reaction, delta G is positive. Because if delta G is positive, the reaction is not feasible. So we say delta G is equal to delta H minus T delta S. You've got to remember that equation for delta G, because that's always the key to this kind of question. And it gives us the value for delta H is plus 178 minus, well, the temperature, 25 degrees C. Remember, the temperature's got to be put into Kelvin, which means we've got to add 273 onto the degrees C. That's something you've got to memorise. To convert degrees C to Kelvin, you add 273. So the temperature is 298 Kelvin times delta S. Well, we just dealt with that in the first part. So times 0.165, and it's plus 0.165. That should be a positive term there. So minus T delta S is minus 298 times 0.165, and if you calculate that, you get plus 129 kilojoules per mole. And then you just need to explain that because that's positive, that shows you that the reaction isn't feasible. Okay, because delta G that you've just calculated is positive, the decomposition isn't feasible, and therefore the calcium carbonate is stable. The last step is that it says, well, what's the minimum temperature at which it could decompose? And the way you do that is again to start with your definition of delta G. So delta G is delta H minus T delta S. And the temperature at which decomposition first becomes feasible is the temperature at which delta G stops being positive, and is just about to become negative, and therefore is equal to naught. Okay, so what we say is that at T minimum, the temperature at which decomposition just becomes feasible, delta G is equal to naught. And if delta G is equal to naught, it means that delta H must be equal to T delta S, so that when you subtract them they cancel each other out. Okay, so that means that delta H is equal to T minimum times delta S, and therefore delta H divided by delta S is equal to T minimum. And you just plug the numbers in. So delta H is plus 178. Let's get rid of this so we're not getting crowded here. Delta H is plus 178. Delta S is plus 0.165. And you work that out and you get 1079 Kelvin is that ratio. And that would actually do as your answer, because it doesn't specify what units you've got to put it in. But if you wanted to put that in degrees C, remember you just have to take away 273, so that is equal to 806 degrees C. And that's the end of that question.